what we're doing today, first off, my name's Matthew Taylor. Those of you that don't know me, I've been in the supermarket world for, I don't know, 25 years, something like that. What I want to do today is talk to you about the differences between air conditioning, particularly residential, and supermarket rack, parallel rack refrigeration. What is that, right? So the target audience here is if you have experience working on residential systems, commercial air conditioning systems. You hear guys talking about racks, you hear guys talking about subcoolers, you hear guys talking about all this stuff. What are they talking about, right? Is this something that's interesting, right? Is this something that's terrifying? What's going on here? I think what you're going to find as we go through this, you already know a great deal about this. You just physically it looks different, set up a little bit differently, but the concepts are the same, okay? We're using direct expansion refrigeration, right? That's the same thing we're using in residential. So that's our goal. That's what we're going to cover today. We do have a fairly small group, fortunately, so we can, if you've got questions, ask them, right? We'll deviate a little bit and cover some stuff that you might be interested in that I'm not presenting, okay? So one of the first things, let's talk about the major pieces, right? When we think residential, we got a few major chunks. We got that indoor unit, right? What does that look like in the supermarket world? Well, we've got an indoor unit too, okay? And you've seen it. You've all been grocery shopping, so you walk right by our indoor unit, all right? Our indoor unit is a refrigerated case in most instances, all right? We're gonna have the same major components. In your air handler on a residential system, we've got return air, we got supply air, we got a blower that's making that happen. We've got an evaporator coil, right, where our refrigerants can change state because of our metering device. We got liquid refrigerant coming in, we got our suction going back to our compressor. I've got all of that going on inside these cases as well, right? So that part just looks different. And we'll break it down and look inside one of these cases as we get through this a little bit. All right, so the other thing we got an outdoor unit, right? Well, guess what? We got an outdoor unit too, okay? Ours gets a little bigger in the supermarket world, a little more complex, a little more things going on inside. But we're going to contain the same major components. You've got your suction coming back to your compressors. You've got your liquid leaving, going into that indoor unit. We're doing that as well. You've got a compressor. We've got a compressor, right? We'll have a compressing unit. We'll talk about that in depth. You've got a condenser, right? You've got condensing fans. You've got controls that are turning all that on and off. All that's inside your outdoor unit, okay? We're doing exactly the same thing. Our form factor is, like I said, is larger, okay? So when you hear a guy talking about a rack house, when you hear those words, this is what he's talking about. This is a big metal box about the size of an 18-wheeler, about as big as you can move with an 18-wheeler. That's my outdoor unit. It's going to have all those components inside of it. This particular one that I'm showing you a picture of here actually has two racks. It's one rack house. It has two separate racks inside. Then you can see on top, I've got my condensers, right? That's kind of a typical setup. Another version you might hear of the motor room, okay? We may have exactly the same equipment, but it's actually in a room inside the store. You walk in, you open the door, turn on the light, there's all your compressors. The only thing that'll be different there, my condenser will be on the roof, right above it, okay? So that's a rack house versus a motor room. You may hear a dog house, okay? That's when we've shrunk this box down really small. We took out the space for the people, and we mounted this on the roof, and the doors open from the outside, so I can work on everything. I can go all the way around it and open all the doors. We call that the dog house, okay? So that's that terminology. That's what it looks like, all right? And then your third major piece that you have is thermostat, all right? Well, I want you to think of this thermostat a little bit differently, okay? My thermostat has sensors. It's got a temperature sensor. Modern thermostats, most of them have a humidity sensor built right into them, right? So they're reading the temperature, they're reading the humidity in the space that it's mounted in. Well, they may also have a wire that runs outside and is reading outdoor, or maybe even pulling that off the internet today, right? Getting the local weather report, basically, and it's going to display that. Those things that are coming into that, think of those as inputs, okay? Then I've got a decision maker. I've got a computer that's comparing those inputs to the values that I want, my setting, my temperature setting, 72 in this case, right? And deciding what to do about that. It's making a decision. So I've got a decision maker who's going to read those inputs and decide I need to take action or not, okay? And then it's going to turn things on and off, right? Well, that's its outputs. So I've got inputs coming in, I've got some decision making going on, and then I've got some outputs, right? That's really what my thermostat is doing. Well, in supermarkets, guess what? I'm going to do exactly the same thing. I'm just going to do a lot more of it, all right? So right there's my big decision maker, okay? And then over there on the side, you can see I've got modules. My modules are going to have inputs. They're going to have those temperatures from the cases coming into them. They're going to read my suction pressures. They're going to read my discharge pressure. All those values are going to come in to modules, and then my brain's going to make decisions based on those. That's my program. You know, what do? I turn on my case. It's running too warm, right? So it's got to have some outputs. It's got to have a way to do that. So on my module on the other side, I'll have some outputs, okay? Why is that not all self-contained? Because I got a lot of them. I got way more than physically will fit, okay? So what am I talking about? Well, on a typical rack, I could have between 20 and 40 cases is not uncommon, okay? That means I've got 20 to 40 temperature sensors alone, right? And if you think about the size of a grocery store, that's a lot of wire. If I'm going to pull that wire all the way from that case all the way out to that rack, that's a lot of wire. Well, what I can do instead is set these modules up so all those wires can come into one place, and I can mount that module fairly close to those cases. Then I can just run one communication wire, right? It's a lot simpler. So that's what we're going to do. We call that a network, okay? And I can have a lot of these modules. I can have a bunch of them, right? I'll have one for my condenser. I'll have one driving my compressors. I'll have one running all those cases. I'll have one running defrost systems. So that side gets complex. But if I break it down into the basic function of this thermostat, it's exactly what it's doing, right? It's reading 40 case temperatures, but I'm only really concerned with this one that's running warm. I can think of it, break it down just like a thermostat. It's one input. There's a program in there that's telling it what to do because of that value, and there's one output. I'm turning on that case, right? So if I break it down simply like that, it works the same way. All right, so how about that? Has anybody ever seen that before? Right, okay. I'll take you through it, Brian. All right, well, guess what? We use this too. This is our bread and butter right here, okay? The exact same, all right? We're going to add a few more pieces and parts in here. We're going to manipulate these pressures and this refrigerant a little bit differently, but for the cycle to work, we must achieve exactly the same thing that you do in residential or commercial, right? So I've got my compression. I'm going to discharge out of my compression as a hot gas, right? It's going to be a superheated hot gas. It's above its condensing. We've added a little extra heat there. That's my heat of compression from my compressor. Then when I go into my condenser, I've got to reject that heat, right? So I'm going to run my refrigerant through there until I cool that refrigerant down back to saturation, and then it's going to condense. We're going to do that, okay? Then I'm going to come out of that as a liquid, right? I'm going to send that liquid to an expansion device. This is going to be the breaking point between my high and low pressure side of the systems, right? I'm going to do that, and I'm going to control how much refrigerant flows into my evaporator with that metering device. Now, that refrigerant is going to flow into my evaporator. I'm going to bring what I'm trying to do, what's the point in this whole system, is bring in some warm air and let it come out cold, right? That's what we're doing in air conditioning. Guess what? That's what we're doing in refrigeration, the same thing. We're going to absorb that heat, and it's going to cause my refrigerant to change states. I'm going to have that latent heat exchange exactly the same, and that's going to absorb all that heat into that refrigerant, and it's going to come out as a dry superheated vapor, right? Yeah, we're going to do that too, and we're going to send it back to our compressor, okay? So I'm going to take you through what that looks like, all right, on our side. You know what it looks like on air conditioning? Let's take a look at the way this looks. Start with compression, all right? So here's my compressor, okay? Now, once again, this can be a little intimidating, a little scary. Got a whole rack full of stuff. Let's talk about it, break this down. Just like that EMS, just like that thermostat we were talking about, this actually is fairly simple if we break it down into its little pieces and parts. So the first thing to note is, well, there's actually a metal stand that these compressors are sitting on, in this version, okay? That is our rack. That's why the name, all right? Wow, yeah, just blew away a whole lot of mystery, right? And that's not exciting at all. That's what it is. That's why we call it a rack, okay? So what we've done is we just take a bunch of compressors and we're gonna pipe their discharges together so they have one common discharge. We're gonna pipe their suctions together so we have one common suction. Well, when we do that, what we actually create is one very large variable capacity compressor. Well, residential guys are seeing variable capacity, right? Two-stage compressors or compressors that ramp up and down with VFDs, or you're doing that now. Well, so are we. We're just doing it old school by having different size compressors and different amounts of compressors running. If I need a bigger compressor, I just turn on another compressor. If I need smaller compressor, I just turn one of them off, right? And the whole unit acts as one compressor. So I can make it very small or very large based on my load. That's it, okay? The only time I've got to break that down farther than that big idea of just a variable speed compressor is when I've got to actually work on the one compressor that's tripping out an oil or having some kind of mechanical failure. Then I've got to dig into it and think of it differently. But most of the time, I'm just thinking this is my compressor unit. I need a bigger compressor. Why isn't it staging up, right? I need a smaller compressor. Why isn't it turning off, right? And we'll go through those processes as a technician troubleshooting. But that's the general concept. There is one other thing I want to point out on this slide, and you'll note that on each of these compressors I have this blue thing that you're probably not real familiar with. Maybe you are. This is an oil control, right? And we're going to talk about the oil system a little bit later, but this picture demonstrates it pretty well, so I just want to point that out. Hold that in your mind until we get to it. So that's compression. All right, so the next piece is your discharge line, right? We come out of compression as our hot gas. We talked about that, superheated refrigerant with our heat of compression inside of it. Well, in residential, we're not doing a lot with this line. We're going to have a high pressure switch, right? Guess what? So we'll mark it. We'll have a high pressure switch in there. And then you're probably going to see especially down here in Florida, reversing valve. You're going to have something like that in there. All right, we're not going to do the reversing valve idea. That's really cool. It's one of those unique things for heat pumps that we just don't do in markets. So we are going to do some other stuff though, and this is a change. So my hot gas comes out of my compressor, and then one of the first places it goes is this oil separator. Okay, so just want to talk about that for just a moment because this is different. This is one of the places where it doesn't really relate very well to residential. It's the next concept. So in residential or packaged commercial air conditioning, your oil, every compressor gives out some oil with its discharge, right? Well, that oil is going to go through the entire refrigeration cycle and then come back in through the suction, okay? In the supermarket world, we've got a little bit of that going on. We have some oil that goes through every component all the way back around. So that part's the same. But the reality is, if we're doing that on a large scale, we're losing a little bit of efficiency when we do that. Our evaporator's got oil in it. It's not exchanging heat. Our condenser's got oil in it. It's not exchanging heat, right? And our compressor is using compression to move it unnecessarily, right? Not only that, but my compressors, when I pipe them all together on the same suction line, they're not going to pull the exact same amount of velocity, right? Because they're different sizes, and I can unload them and load them. One may be 20 years old, one of them I just changed yesterday. So they may be pumping different amounts of oil, they may be pulling in different amounts of oil. So I've got to have a way to very precisely control how much oil is in each compressor, right? So the first thing I want to do is remove a lot of that oil so it doesn't go all the way through my system. That's my oil separator. That's this guy right here, okay? My hot gas is coming in, my hot gas is going out, all right? A lot of that oil, not all of it, but a huge amount of that oil is going to separate. And then I've got to have a place to store it. So when a compressor needs oil, it has it to use. Well, that's my oil reservoir. I'm going to have that system over here. And it's just going to store that extra oil so when a compressor calls, it gets it, okay? And then that's going to feed the blue thing I showed you on the front of the compressor just a minute ago. That's the oil control, and it's going to maintain the right level of oil inside the compressor. So this is a change, right? This is one of the few things that's just really different about it. When I move through the cycle after that, I've got a couple more things I'm going to throw in here. Now, these are actually fairly simple. We just need to know, all right? The first one is this three-way valve. What's going on here? Well, just like your reversing valve is allowing you to send your heat somewhere else, right? We're going to use that same idea. Because I'm creating heat that I have to reject to the atmosphere, that takes work to give away energy, right? I'm trying to get rid of it. I'm not using it, right? Well, this three-way valve is going to give me an opportunity to actually use it. If there's somewhere that I need heat, I'm going to use a three-way valve and make that heat go there instead of just rejecting it outside when I need it, right? Might not always need it, so that's why I've got a three-way valve there, so I can kick it back and not use it when not necessary. Some of the common things that we see, particularly down in Florida, we see a lot of water, right? Every grocery store's got to have hot water. Well, I can heat it with my rack, okay? Makes sense? Another thing that we'll see really just about everywhere, dehumidification. We've got that reheat coil inside a dehumid, right? Where's that heat coming from? We can use this to reheat that air. Up north towards the Great Lakes, I've seen this used as a coil in front of the makeup air unit because it might be negative 10 degrees outside. Might want to heat that air up a little bit before I use it to repressurize the store for my exhaust fans, right? We can put a coil right in front of it, and when that's necessary, kick it on. Okay, so I've got that going on, and then that heat from that reclaimed heat comes back. And it goes right through, the rest of it goes through my condenser, okay? Whatever I didn't reject. Another feature that we see, this set of valves here, this is my hot gas line, that main line where all those compressors, right? I've come out of my oil, I've now come out of my heat reclaim, and you see it splits. So a very common thing that we do, your air conditioner, if you got straight AC, you're probably not running that in January at 2 o'clock in the morning when it's 17 degrees outside, right? Well, we are going to run refrigeration, right? Because we still need that ice cream to be frozen. Even though we're heating the store to 68 degrees, I got to cool this stuff down to minus 10 because the store is at 68, even if it's minus 10 outside, right? So that means I've got to be able to run my rack in low ambient conditions. That's a little bit of a change there. So one of the features that we have on our systems to make that possible is the ability to turn off half of my condenser, make my condenser half the size that it normally is. So we split it in half, and we call that the split. If you hear guys talking about a split condenser or the condenser is in split, something like that, what they mean is instead of having 100% of my coil, I've turned off half. I've closed off half. So my condenser is now smaller, okay? And we do that in low ambient. A couple ways to do that. We can do that with another three-way valve. This setup is 2 solenoids. And you notice there's no coil on that one. They're normally open solenoids, and we just have 2 there so that the flow is perfect through both. They're exactly the same. That's really the idea. Okay, so that condenser. Let's talk about that for a minute. All right, well, there it is. This shot of the condenser is from a rooftop looking down on that same rack I took a picture of earlier. You'll see the 50% splits right there, right? You can tell this condenser is actually 2 condensers split right down that line. That makes it a little clearer, okay? The other thing that we've got is a whole bunch of fans. Well, we may have 2. We may have 12. Totally depends on the application and how large this rack is and the ambient that it lives in. Miami will have 2 more fans than we will in Michigan. It's just how that works, okay? So when I look at this, the other thing we're going to add to this, once again for that lower ambient setup, when it gets cooler outside, I'm going to start turning off fans. I'm going to stage my fans. Okay, so when temperature drops, when I just watch my discharge pressure, and as that discharge pressure falls, I'm going to start shutting off fans to keep it up. Right, I got to maintain that pressure differential across that expansion valve. So I'm going to do that through staging my fans off. Is the old school way of doing this, and it's the most common, right? Another is let's keep all of our fans on and just slow them all down, okay? That's the more modern version. This is what we're seeing, with newer construction. This particular one was a retrofit that was done probably 10 or 15 years ago. That's also fairly common. That's a VFD, variable frequency drive, can do that, right? Another is B&E motors. I can send it the 0 to 10 volt signal that tells it where to run. Yeah, why not, right? The motors are more expensive, they're a little heavier, but it works fantastic, and I don't have to worry about a VFD and lightning and all the things that, the downsides of that. So that's a more efficient way to do it. We're seeing that, like I said, more and more. That's becoming very common. All right, so when I come out of my condenser, I'm liquid, right? Here's a pretty big change. So when you're charging a residential system, probably doing that off subcooling, right? It's pretty common. Because your system is critically charged. And what I mean by that is you don't have a liquid receiver. So if you add more refrigerant, you cause that refrigerant to back up in your condenser, right? You start holding more liquid in the condenser. When that happens, you're subcooling more, right? Yeah, we're not going to be able to do that. So my liquid line is going to get a little different. There's a few things we're going to do here different. First thing I want to point out is receiver, right? That means it's not critically charged, okay? This is a little bit of a change. This is common in small refrigeration. This isn't particular to a rack system. But if you haven't worked on small refrigeration, you're only air conditioning, then this concept may be a little bit new. So I'm going to talk about it for just a minute. So what I'm going to do is I'm going to take that liquid coming out of my condenser, I'm going to put it into a vessel, okay? That vessel is going to hold extra. So if I have things that turn on and off, need more refrigerant, if I need to put some in my condenser because it's really cold outside and I need my condenser to be smaller, I have that extra refrigerant to do that, okay? But that's going to have a few consequences. One, if I'm running at 20% receiver, 30% receiver, and I add another 150 pounds of refrigerant, I will see no change in pressures. My receiver is just going to have an extra 150 pounds in it, right? So I can't control discharge, I can't control suction, I can't control my superheat, can't control subcooling by adjusting my charge, right? That's a big change, okay? That means I've got to be able to do all those things in another way, all right? So we'll dig into that in a minute. You will notice that on your liquid line, you probably got a dryer, right? Yeah, I do too. I'm going to have a dryer filter dryer set up in there. All right. Another piece that I'm going to have some type of valve in that liquid line. And I just said we got to have another way to control some things. Well, my discharge pressure, because I may make my condenser as small as it'll go. I may turn off all of my fans, and it's just really cold. And there's a nice wind blowing through there, acting like a fan, moving that refrigerant through my condenser. So how am I going to control that? Well, I'm going to have a valve on that liquid line that's going to cause that refrigerant to start filling up that condenser, making it even smaller because it's now got liquid in it, okay? We call that the hold back valve, right? So I'm going to have a hold back valve on this system in South Florida. We're probably not going to see that come into play very often, right? But as you start moving north, even I-10 right here in Florida, we will have nights where that comes into play. When we start going north of there, we hit the Great Lakes, we're running this guy 6-9 months out of the year at night, particularly, right? For sure. So it's a big piece there. It acts kind of like a headmaster. There's another valve that we use for the hot gas side that does exactly what a headmaster does if you're familiar with that. Once again, that's more refrigeration on a small refrigeration system. All right, so another piece that is going to be different. I told you we can't adjust our charge and cause subcooling. Because my receiver has got liquid and vapor in it, it's at saturation, right? So all that subcooling I would have done in my condenser, lost, right? I'm at saturation. Can't be superheated, can't be subcooled. I have vapor and liquid present. I'm at my PT chart. Right? Does that make sense? But we probably want a little bit of subcooling. we want to guarantee that we get that full solid column of liquid to my expansion device, right? And in this pipe, going from here all the way to that farthest case, maybe a couple hundred feet. Nice, that's not uncommon. So I've got to cool it down a little bit more, right? Or I'm going to flash, especially when that liquid line goes up into the ceiling across that hot store, you know, the heat rising in that store. Probably going to cause a liquid flash. So I want to subcool it for that reason, right? There's a couple more reasons I'm going to do that. I can add an incredible amount of efficiency on my low temp particularly if I subcool it at a medium temp. So I want to subcool. Every BTU I'm taking out of that liquid is equal to one that my compressor's got to do. So I'm going to try to take advantage of that with a subcooler. And then the third is if I subcool that liquid, because the liquid then becomes more efficient, I need less of it, I can undersize my liquid lines. I can undersize my TXVs. I can undersize my suction because I'm not moving as much refrigerant, because the refrigerant I have is more efficient because it's subcooled, all right? To do that means I'm going to really subcool it, all right? And if you notice, my liquid lines are insulated. There's something you don't see. Why is that? Well, because I've done all this work with a mechanical subcooler. That's what this is. I'm going to bring that liquid maybe down to 50 degrees, right? Some CO2 stores I've seen 20, 30 degree liquid, right, below freezing, right? That's some subcooling. We're getting some extreme subcooling, all right? So how are we doing that? This might be new to you, don't know, depending on your background. It's just a plate heat exchanger, okay? Some of you guys up north right now online are going, yeah, we got, you know, we do this all the time. Some guys down south, Florida, might be going, I really hadn't seen too many heat exchangers, you know. So what do we got going on here? Just a plate heat exchanger. One side, one half of this thing is an evaporator. It's going to be piped to my rack. I'm going to feed liquid to a TXV, right? It's going to boil inside. It's going to absorb heat. What's it absorbing heat from? The other half. Well, in this case, that's going to be my liquid coming out of my liquid receiver. I'm going to run it right through that evaporator. It's going to go in warm, come out cold. And I'm going to have a load rated in tons, BTUs, right? Just like anything else, on how much heat it can absorb, okay? That's a mechanical subcooler. That's it. No moving parts inside. We have an expansion device. That's about the only thing that's gonna move in this whole setup. I threw this guy over here just to point out that anytime we're looking at mechanical valves, there's another one up there. Anytime we see those mechanical valves, that's the majority of what we have out in the world today, and they are slowly going away, right? We're replacing with electronics, okay? Electronic valve and a valve driver, right? Super common to see that. This particular one that I'm showing you is a retrofit on a 20-year-old rack, you know, and we've added electronic device, electronic valves. Why not, right? It just makes it more efficient. Doesn't really matter how old that it is. All right, so I'm coming up on my metering device, and you guys probably recognize that. That little shadow of an expansion valve, right? That's what that is. Well, how about that, okay? It's an expansion valve. Inside each of those air handlers I showed you, you know, my display cases, every one of them, every evaporator coil has got to have some type of metering device. The most common that we use, 85% or so out there today, are mechanical expansion valves. Nothing new there if you're familiar with expansion valves. All right. Our version is probably the kind that you know, your AC guys are saying, we don't really use that too much anymore. We use them heavily. We got a strainer to keep it clean. We've got a nut we can take off there and a stem we can adjust. Right? That's kind of standard. Now, not all of them are that way, but that's kind of the standard because our system is so big, we can easily get some debris in that system. And I told you I'm going to have 40 some cases, right? That means I could damage 40 TXVs, so I'm probably going to throw a strainer or something in there to catch that, right? And then the other thing is I got to tune that evaporator exactly, the amount of airflow that's flowing through it to match the refrigerant flow. So I'm going to want to have control of that superheat, right? So I want to be able to dial it in and get it just right. So it's going to have a manual stem most of the time, okay? Then the next thing you see right next to it, electronic version, okay? This is a bipolar motor. We're seeing these really heavily in refrigeration in a lot of different places, right? My mechanical expansion device has an orifice, and it's got a pin, right? The pin plugs the hole, and that makes no flow, and then I just open that pin up, spring pressure and all that. It allows more refrigerant to flow through. Well, I'm just making a hole bigger or smaller. Well, that's what I'm going to do with my electronic also. It's just going to be a motor that turns like a screw, threads in, threads out, closes that hole up or makes it bigger. Okay, we're seeing those used, great deal. And then we got this new guy. I say he's new. He's been around probably 15, 20 years, but not real common in our world until CO2 came along. Really, we started using this for medium temp CO2 applications, and if you heard Trevor talking about CO2 earlier, he'll say, if you can do it in regular refrigerant, you can do it in CO2. Well, guess what? That works backwards. Started using that really heavily in CO2, and everybody's like, why aren't we using this with 404 and 407 and 22? Why not? Guess what? It works. It works just fine. And it's way simpler. So I would not be surprised if we don't see a jump, something like this into the air conditioning world. All this guy is a solenoid. He's just rated to millions of clicks. And his hole inside is smaller than a regular solenoid. He's a restriction, okay? And all I'm going to do is I'm going to use a computer to measure the superheat on the outlet of my evaporator and tell that guy, hey, open for 2 seconds and then close. Right? I mean, it's just that simple. You'll hear it clicking. You walk through a grocery store today, you got new cases, shiny stuff, you're probably going to hear click, 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 click. Right? That's what's going on. It's just pulse valve. Pulse valve is the name of it. So let's talk about our evaporator for a minute. All right, our evaporator is really not that much different. I'm going to show you a picture of what one looks like here in just a minute. But I do want to talk for a moment about why is refrigeration so much colder than air conditioning? How do we do that? This isn't unique to racks. This is just the concept. And then I'm going to throw in there a little bit about how we're controlling it. Okay, so my evaporator is the same. I've got a metering device. I'm going to blow air through there, right? I'm going to bring heat to it via air. It's going to absorb that air, boil my refrigerant, right? I've already covered that. We're going to do exactly the same thing, right? But one of the differences is, I told you we can't adjust our charge to control our suction, right? Suction is everything in this game, in refrigeration. So the reason that it is, and what we're going to do about that is because of our PT chart, right? I just talked about saturation, right? When we're at saturation, we equal our PT chart. Well, inside my evaporator, I got vapor and liquid, right? I'm at saturation. That means I can control the temperature of that evaporator by controlling my pressure directly. That's huge. This is the key piece that is different from air conditioning to refrigeration. I'm going to control very precisely the temperature of that evaporator. I'm controlling the temperature the refrigerant is going to boil at because of the PT chart exactly by controlling my pressure. That will be the temperature that refrigerant boils at. It's predictable. Got a PT chart on my phone, right? This works in air conditioning, right? You guys know that. The differences in refrigeration, it's really critical and very important. We live on the PT chart, okay? You guys, you use it occasionally, right? We're using it constantly, okay? That's really the biggest difference. Now, what that means is I can control my suction pressure by how big my compressor is, not my charge, right? So if I'm sitting here with a 40 PSI suction coming out of my coil, and I need it to be 30, I make my compressor bigger. Will that not cause my suction to fall? Of course, right? So I'm going to stage on my compressors based on my suction pressure. That's what's going to control whether I need more compressors or less, right? If I'm trying to control 40 and I'm down to 30, I'll turn off one of those compressors on the rack, right? I'll stage down. I'll have a smaller compressor. That'll cause my suction pressure to go up, right? So I'm going to maintain a very precise suction pressure. The whole control, my thermostat, is not my case running warm. My thermostat is my suction pressure. Is it too high? Is it too low? I'm going to bring on things, compression, to maintain that suction pressure because of that PT relationship. All right. Another piece about that, because my airflow is not all over the place, it's a very defined, very small space, and I'm recirculating the same amount of air, I can also predict very precisely how many degrees different between my boiling temperature and the air coming out of that supply grill. Right? When you guys in the air conditioning world talk about TD, you're usually talking about return to supply. Right? When you hear rack guys talking about TD, they're talking about my coil temp to supply. It's a very well-known number, right? It's engineered. Okay? It's printed on the tag of the equipment. So if I'm trying to make 32-degree air come out of that supply, that means that my evaporator must be 22 degrees. What pressure is that? I get out my PT chart with my refrigerant type. That's my suction pressure. I put my gauge right there, and it'll tell me whether I'm going to achieve that or not. Right? That's how we do it in refrigeration. Work it backwards with that TD. My supply air requirement gives me my evaporator requirement. My evaporator requirement, you run the PT chart, tells me the suction pressure I must be at. Right? Does that make sense? Superheat? Yeah, this guy controls superheat. No difference. Right? Why am I using superheat? To protect my compressors. It's the only reason. It's a loss of efficiency, right? But it's a safety I have to have built in, so I don't try to compress a liquid, right? We're doing exactly the same thing, right? That's exactly the same. No change there. Okay, so that's what refrigeration is. This is what it looks like, okay? So that first picture I showed you with all the pretty produce in it, you know, all the pretty stuff being displayed to sell. In the service world and installation, we don't see it that way. This is how we see it, right? So if you notice, that's that multi-deck case. This was all my product that was hanging there. That was all pretty, right? This particular case, we've taken all that out, okay? There are pans that cover this bottom chunk here. We've taken the pans out, right? So you can actually see inside what's going on. Well, I've got this little drawing here. So you can see, I got a plenum. Look how small that is. It's tiny, right? I got fans, and I'll have multiple fans across here. This particular one's a piece of cardboard covering a hole because the tech didn't have a fan. He had a fan that went bad, and he had to cover the hole so it wouldn't recirculate air through the plenum, right, to try to get by, okay? That's what was going on. This tech that took this picture was changing the fan motor, right? So that got him through the night, and then in the morning, the guy came back with a fan motor. So he had to pull that so you could see it, right? I've got supply, I've got return, right? This is my supply here. My return is down here at the bottom. And now when you guys are walking in grocery stores, you're gonna be looking for that little grill, right? You're gonna see it. That is the return, right? So that means this whole space is return, and then I'm gonna force that air through that coil. Sounds kind of familiar, right? And then I'm going to go up the plenum of the back wall, all right? And I've got supply grills. I got little holes all along the back of this case that's going to let some of that refrigerated air come out there, and it's going to bounce off those shelves, lose its velocity, and then I'll have this main air curtain coming straight down. That air will blend right in with it and go right through the return. It's going to recirculate, okay? That's why I can predict the temperature of that supply air, because I'm not spilling, if everything's working correctly, I'm not spilling a huge amount of air out onto the sales floor and then pulling in nice, warm, moist air, heavy load, that I'm going to try to refrigerate. I'm recycling the majority of my air, so I can predict that 10-degree difference, or 8-degree, or 6-degree, whatever it might be. All right, so something else we're going to see on our evaporator are fins. So as you guys probably know, the more fins I can cram in per inch, the more efficient the system is, right? The less energy it requires to do the same amount of work, because you're making the evaporator bigger by having more surface area. But there's a downside to that. You can't go too far. In residential, that's probably limited by dust and cat hair, right? You start stopping that thing up. In refrigeration, well, I told you kind of a standard TD that we call coil temperature to air supply air. It's about 10 degrees. Well, can you think of refrigerated cases that run warmer than 42 degrees? No, they're all way under that. So that means most of our evaporators, if not all of them, are below freezing. They're below 32 degrees. So in a residential air conditioning system, you've got a condensate system. When your air conditioner is running, it's producing condensation constantly, right? You get a nice steady flow of water coming out of that condensate pipe. Refrigeration works a little differently. We're continuously doing the same thing. We're pulling moisture out of the air all the time. The difference is it's not running out the drain. It's frost. It's going to freeze to that coil because it's below freezing, right? So if I make water and I'm sitting here at 22 degrees, yeah, it's going to stick. It's going to be white frost. So that means I've got to defrost it, right? I've got to shut off my refrigeration, and I've got to add some heat. May just be recirculating the same case air, and that's enough. That's warm enough to melt it. May have electric heaters in there to kick them on. Maybe using hot gas, using my hot gas coming off my compression before I go to the condenser. I can run that through there, kind of like your reversing valve idea, right? Run the hot gas through that evaporator and melt all that ice out of there. But I've got to manage that somehow, okay? The colder I get, the faster it's going to grow snow and ice, right? So when I go to medium temp, you'll see it's not uncommon 6, 8 fins per inch, something like that. It's kind of a standard. When I go to ice cream, I'm running at minus 25 degree evaporator, minus 15 degree supply air. That's where we run, right? All that fat and sugar didn't make it hard. It's got to be that cold. When I do that, my fins are going to go to 4, right? Wow, yeah, you can drive a truck through there, right? You start seeing some pretty big sized gaps. So the colder we get, the more gap we have to have because we're going to grow more and more snow and frost, right? If the frost on 2 fins touches, it grows enough that it touches, I got a stopped up evaporator, right? It's the same thing as your evaporator full of cat hair and dust. How well does that cool? Yeah, no, it turns into a block of ice. Well, that's what's going to happen to mine too. It's going to turn into a giant block of ice. My defrost won't be able to handle that much, right? Once I shut off that airflow and it starts growing ice, I'm out there with hot water, right? Trying to melt it out. It's a service call, okay? But when I am in defrost, I'm going to melt all that, right? All that I'm supposed to anyway, if everything's working right. I'm going to melt all my frost. I'm going to melt all that ice. My condensation system is now going to get a flood, right? It had nothing going on for 6 hours because it was all frost. Now I kick on my defrost, and I got a lot of water coming out of it, right? So my plumbing is probably actually bigger than what you would see on a residential system. You know, it's not uncommon to see inch and a half pipes under each one of these little 8-foot cases, right? Why is that? Because it's all at once, right? My ice cream may only defrost once a day. It's 24 hours worth of snow and ice, right? Going down the drain in 30 minutes. And then it's not going to flow in again. So I get a little flood and then I get nothing, right? That's one of the changes that we see. All right, so talk about our suction line, okay? So that's coming out of our evaporator. Now we've got a suction line. On your suction line, you're going to have a filter dryer sometimes, right? That's about it. Not a whole lot going on there. We're going to throw something else in there. We're going to add a really important device, and this device is called an EPR, and that means evaporator pressure regulator. Right? What we're doing with an evaporator pressure regulator is exactly as it sounds. We're regulating the pressure in our evaporator. I just described that we're controlling the temperature of our case by controlling the suction pressure, right? So what do I need this for if my compressors are all staging on that idea? Well, it's possible, not only possible, extremely likely that not every single one of my cases on this entire rack run exactly the same evaporator temperature, right? I could have ice cream, I just told you, running that at minus 25 degree evaporator, right? My French fries, I'm gonna run at minus 10. Okay, so how am I gonna control different pressures on different evaporators? I'm gonna put a valve in there. That's how I'm gonna do it, all right? This particular one is super common. It's a mechanical valve. I can adjust the spring inside. I won't go through all the details of that valve, but the concept is I can adjust this and I can raise my pressure. I can't lower it lower than my compressors, right? But I can raise it above. So what I'll do is I'll look at my coldest evaporator on this entire rack. That's what I'm going to set my compressors to run at. And then I'm going to manually dial in each one of these valves to match exactly that evaporator. Okay? Just to make things a little more complex, not every single case is going to have an EPR. What I'm going to do is I'm going to group them together. And I'm going to do this because I can run a lot less pipe through the whole store. And I'm going to do this so my controls are simpler. I told you I have 40 cases, right? I don't have 40 suction lines and liquid lines running all the way back to my rack. I'm going to group them, okay? So if I walk into a grocery store, I see doors, glass doors, frozen food on one side, ice cream on the other, bunch of them, right? Well, I'm going to take about 6 of those, and I'm going to group them together, and I'm going to run one suction and one liquid line big enough for all 6, okay? And we call that a circuit. So when we're talking about a circuit, we're talking about all these brothers or sister cases that are tied together, right? They're going to defrost at the same time. They're all going to go into defrost together. That way I only need one set of controls to turn them on and off, right? I'm going to refrigerate them with the same liquid and suction line. That means I'm going to have one EPR controlling that suction pressure to all 6 cases, right? So it just makes it a little simpler. Makes it a little cleaner, right? So that's my EPR. I've got a modern version. You knew that I would, right? So all I'm doing here, same exact idea, concept as an electronic expansion valve. I just have a bipolar motor. It's a screw. And if I turn the screw, it goes in and out, right? That makes the hole bigger or smaller. That causes a restriction, causes that refrigerant to back up inside that evaporator, causes the pressure to go up. If it goes up too high, I turn the screw, open the hole, pressure goes down, okay? Pretty simple, actually, when we break it down that way. That's without a doubt where we're going, right? The control is far better. The pressure drop across it, the loss of efficiency is far better. Everybody is going to eventually end up electronic, but there's so many out there. You know, the mechanical valves are going to be around for a long, long time. And anything new going in today is going to have electronic valves driving it. All right, so here's another piece. There's my filter. There's my suction, right? Probably not running that all the time. Definitely going to put something in there when I'm doing construction or remodel, stuff like that. I'm opening the system up. I want to catch all my debris from that process, but most of the time that's empty. Now, I've got a suction accumulator. All right, might see that in air conditioning sometimes, right? This is a little bit of our flood protection is the idea, right? If I've got a, you saw that evaporator fan was missing. I had a piece of cardboard covering the hole. Well, you think that may be flooding a little bit? Yeah, it might be, because I'm not bringing as much heat as that valve is set to control. It's way less. So that valve may not be able to control that, especially that mechanical valve. You know, it's going to close down to its extreme and may not be enough, right? My electronic valve does a lot better at that. But my accumulator is going to give me that last bit of protection just in case I got a little bit of flood back. Because if I have some flood back, remember I got 6 compressors on here, not 1, right? I'm not damaging a compressor. I'm damaging a lot of stuff. So I'm going to throw a little extra in there. Now, looking at this picture, anybody notice anything that's kind of alarming? That's my suction line. Ice. Yeah, he picked that up right away, right? Do I have a problem? What's that? Yeah, could be, right? So this is another thing that's a little different, all right? When I walk into a rack as a refrigeration guy and I see snow and ice, it's probably not setting off the alarm bells that it probably would for you guys. To me, it's I better check that. It's not, oh no, I got a problem, right? It's I need to check it, okay? Why? Well, I just told you I'm running ice cream at minus 25 degrees. If I'm superheating that refrigerant, that means I'm bringing this refrigerant back. Could be as low as minus 10, right? This rack house might be sitting outside in South Florida in July with humidity. Yeah, You think maybe I'm going to sweat? Yeah, I'm going to sweat. Is it going to be water? Not at -10. It's going to be snow, right? So I don't know by eyeballing this whether it's flooding or not, right? So that means I'm going to be very proficient at taking superheat. In fact, my computer is going to be measuring those values for me so I can just go in and take a look. I'm going to have a temperature probe on my main suction header. I'm going to have a pressure probe on my main suction header. That's what's telling my compressors to come on and off, right? Well, is that not what I need? That and the refrigerant type and a PT chart, I can calculate superheat, right? So I'm going to be checking that. That's what that snow means is, hey, walk over the controller, hit a couple buttons, make sure you're all right, right? If it was flooding, what would it look like? That, right? I can't tell the difference is my point, right? I've got to go look at my superheat and know. All right, so before I get into the next little bit here, that's my refrigeration cycle. That's what it looks like. Anybody have any questions about that? Yeah, go ahead.
The EPR, where does the input for that come from? From the circuit, from the evaporator side?
Right. Yeah, great question. I'll repeat that for the folks online. Where does the input for the EPR come from? Where, you know, what's it measuring? Yeah, an EPR is kind of like a valve that holds back pressure, right? So it's going to sense the pressure on the evaporator side. That's exactly what it's going to do. Yeah.
So I find it pretty fascinating that you have open cases that are 38 degrees, and I'm sure there's an engineered design of like a wind curtain that blocks that. Can you explain a little bit of the principle behind that?
Yeah, right. So so he's asking about that air curtain, and let me just back up to that drawing. It kind of shows it. There we go. So my air curtain is, I'm going to take about 50% of my airflow, and the airflow is going to be way less than air conditioning, way less. I'm going to take about half of that airflow, and I'm going to pressurize the back wall of this case with that air, and about half of it is going to come out of these little holes that you see all along the back. Okay, that's going to leave about 50%. That's going to go over the top, and it's going to come down. Right. The concept here is what we're trying to do is build a barrier between the refrigerated product inside the case and the sales floor air on the outside. We're going to make a wall, right? Now, our wall has to be fluid enough that our customers can literally reach right through it, or we can't sell any product, right? If we make it more stout than that, we're going to have doors. We'll have actual doors that you open and close. But if you notice on those, when you open that door, you still have an air wall, because when that door is open, I don't want all of that warm, moist air, particularly the moisture. Moisture is drawn to cold things, right? If I've got any water in the air, and I do, I got a lot of water in the air, right? We think, I got my humidity under control. Not enough to keep that water from migrating right through into that case and sticking to my evaporator and causing it to freeze up too fast, right? So I want to try to mitigate as much as I can that exchange in temperature and slow that migration of moisture. It's going to migrate anyway, but we want it to migrate as slow as we can. So I do that by creating, you know, somewhere in the neighborhood around 300 CFM is my airflow velocity that's coming down. Okay, that's creating that little wall. It might be high efficiency cases I've seen as low as 150. Right, these are really weak air curtains. If we smoke one of these cases and we can watch that air flow through there, it's kind of cool. On those 150s, you know, the more modern cases, when a customer walks by with a shopping cart and she's walking quick, that smoke follows her, right? It's not strong enough to prevent that, right? Because we're saving power by trying to make it just as small as possible, just barely strong enough. So you won't, my point to that is, you're not going to walk up to one of these cases and stick your hand in there and go, oh, wow, there's a lot of air blowing across my arm, right? It's going to be very subtle. It doesn't have to be extreme, okay? We just want to create a barrier, that's all. Any more than that, we're wasting energy, right? Case will run better, but we're wasting energy.
And just to kind of add to that, sorry, this is one of my favorite things. This is Bernoulli's principle, which is if you have a high velocity airstream, or any velocity at all, you get these eddy currents that go down both sides, right? So you get air that's training on the outside, but it's kind of tumbling this way, and you get air that's coming from the inside, and it's tumbling this way. So it just creates that separation. Because you have low pressure. Low pressure follows that airstream. It interrupts whatever whatever natural currents would be going on in the store. Now, if you have something like a vent that's going through that air curtain, then that can actually disrupt the air curtain and actually, create problems.
Yeah, absolutely. There's a whole troubleshooting process, just like everything else, right? There's a process that if I've got airflow problems, these are the things I'm going to check. Shelves that are too long, the store has violated my load limit, things like that. In the residential world, somebody leaving the front door open and the back door open at the same time tends to cause a temperature problem, right? Because the air is blowing right through the store. Yeah, we got the same thing going on. We got exactly the same thing going on. Somebody violates my load limit, that's causing that supply error, right? When I say load limit, I mean they've usually this bottom shelf is the big one, right? They stock this thing up to here, right? Well, that means my supply error is going to come down and hit that product, and it's going out on the sales floor. Now my case is negative, so it's going to make that air up, right? It's going to suck it in. What's it sucking in? Sales floor air, right? Yeah, we have that exact same, and it's just different, right? It's a checklist you're going to go through each one of these items. That the cause is different, but the result is because of the same problems, right? Leaks in my air system, leaks in my return, short cycling air. Instead of losing it into the attic, I'm just recirculating it, right? Those kind of things. Plenum being tight, sealed, yeah, it's the same stuff. It just looks different. All right, yeah, go ahead.
Sir, case circuits, they have to be made up of a similar temps?
Exactly, right. So the rule of thumb engineers use is they're going to be exactly the same case, right? They may be 4 foot, 6 foot, 8 foot, but they're going to be exactly the same. Practically, does it have to be? Not really. Practically, it needs to have the exact same temperature evaporator, and it has to have the same defrost schedule. So I'm going to turn that refrigeration off and run electric heat or hot gas or whatever I'm going to do. So I need the defrost to line up, right? But my supply air temp doesn't actually have to be the same because I'm only controlling my pressure to the evaporator, not the outgoing air temp. So if I've got one evaporator that's got a 4-degree temperature differential and I've got another one that's 10, but both of them run at 24 degrees, I could put them on the same circuit, right? Because they're both going to evaporate refrigerant at 24 degrees, right? My supply airs will be different. That's a good question. Okay, yeah.
Suction line dryer, would that be upstream of the accumulator and could possibly have liquid go through it, or does that need to be on the vapor side?
So it's traditionally upstream, right? So if you do have liquid, right before it hits the accumulator, it would go through that, right? Now, we can use a dryer in there. Most of the time, it's just a filter, honestly. The only time we would run an actual dryer in that is if we had moisture problems and we were actually trying to absorb that moisture and change them out until they come out dry. That idea, a cleanup, right? Same thing you might do. If we've got a system that's running dry and it's good to go, and we're doing some service work to it, we really want to just be sure we catch, carbon. If somebody didn't flow nitrogen, surely they wouldn't do that. Well, somebody takes a sawzall to a piece of copper, right? Those metal shavings. Yeah, they're going to short out 6 compressors. So yeah, I want to be sure to capture that any kind of foreign material in there. It's really what it's about. Yeah. No, go ahead.
I saw a blue valve in that picture. Is that some kind of shut off to
Yeah.
TXV or something?
Yeah, exactly. So it's very common to have a hand valve to turn off the liquid inside a refrigerated case because somebody's got to clean this thing, right? You guys saw it, that one wasn't all that pretty inside, right? Well, they get a lot worse. So somebody has got to shut off the refrigeration, open up that coil, take a hose to it, right? That's pretty much what it comes down to. So for serviceability, that may not be a refrigeration tech, right? Most of the time it's not a refrigeration tech. We're going to give them a garden hose handle. They recognize it, they know how it works, right? They just turn that handle all the way off. They call their monitoring company or whoever that might be and say, hey, don't call out an alarm on this thing. I'm going to hit it with some hot water, right? Then they unplug their fans so there's no power. They have no refrigeration, no power. They hit it with a hose. When they're all done, they plug their fans back in. They open their garden hose up, right? Turn the liquid refrigerant back onto the TXV. Yeah. Another very good practical question. All right, any other questions about the equipment? Okay, so the last chunk I want to talk about is, so I hadn't scared you off. I sit here and covered this stuff. Now you're maybe a little interested. What's it look like, right? What's it look like? You've heard horror stories, I'm sure. They're all true. Well, no, they can be, right? But let's discuss it. So one of our career opportunities is installation, right? Now, when I say installation, I'm talking about remodels, I'm talking about new stores, I'm talking about just changing out some cases, right? The life of this guy is really different than you know, residential service tech, right? Or maybe even different than a residential installer, right? So these guys, when you hear about guys staying in hotels, traveling a lot, working at night all the time, right, or a lot, that's more along the lines of this, okay? These guys are going to go where the work is, and once again, it depends on where you are, it depends on who your customers are, it depends on the environment, how densely populated your environment is, how much travel that's going to be. But it's not uncommon for these guys to spend a significant amount of time on the road. The other part of this is, you know, these guys are in this store. There's not a whole lot of customers in there, right? So we don't want to do this work during the heavy load of shoppers. It's probably going to be a lot of night work, right? Not all, but a significant amount. Another advantage of this is you don't really have to understand that refrigeration cycle I just went through. These guys who are installing these cases, they're physically moving cases, right? So they got to know how to do that. They're going to seal these cases together. They're going to line them up, get them nice and level. There's going to be an electrician, right? He's going to be wiring all these things, right? That guy doesn't know anything about the refrigeration cycle. I've got an energy management guy. He's got to make all that communication wire work, right? All those computers talk to each other. He may not know anything about the refrigeration, right? So there's a lot of career opportunities in this installation that don't require an EPA card, right? They don't require you to have that really in-depth understanding of everything I just went through, right? There's a piece and a place for dang near anybody who can work with tools in installation, different parts and different chunks of that business. So it's a more diversified group of guys, right? You could have some electricians working next to an EMS guy working next to a painter, right? It's not uncommon for that to happen. So lots of opportunities there on the installation side. That's kind of the general overview. There's exceptions to all of that. There's, you know, all kinds of different versions of this, that, and the other. But that's the general idea, right? And that's kind of what I wanted to cover with you. The next piece I want to talk about, service, right? So this aligns way closer to the life of a service tech in the residential side. These are the guys that are going out to existing systems that have been in service, that are selling groceries, and for some reason they need work, right? Either they can't sell groceries out of this 1 8-foot case, maybe this whole rack is having some significant issues. You know, whatever the problem may be, just like a residential AC tech, right? He's going to get a complaint, he's going to show up, he's going to diagnose the problem, he's going to talk to the customer about potential repairs, right? The customer's going to choose a repair, he's going to effect that repair, okay? So that's really not different, okay? What is different is, you know, he does need to understand that everything I just ran through with you very quickly, very in depth, right? Because he may be faced with a rack down, you know, the whole rack's not running. Or he may be faced with that air curtain is being violated and the case is icing up, right? Completely different problems. So he's got to really understand all of that to be a service tech. What does his life look like? Not very different than residential. You guys here were 24/7, right? Well, the reality is supermarkets, if a refrigeration system shuts down at 2 o'clock in the morning on Christmas Day, there's $250,000 worth of meat. Yeah, somebody's going to go out there and fix that. Is that you? Well, we're going to rotate that call, right? Just the same as you do in residential. So no, you're not going to be on call 24/7. I am, but I ain't going anywhere either. I'm just answering the phone, all right? But my techs, you know, they're going to rotate that call. How many calls do you get at night? How many calls do you get on the weekend? entirely dependent on the customer and what the customer wants. We've got some customers that will pull a case before they send a tech after hours. They don't want to pay time and a half, right? Those guys don't get many calls at all at night. If they do, they're real emergencies. They've lost a whole rack. It's not many, right? We've got another customer. They think they sell a lot of French fries at 2 a.m. for some reason, right? So they call out everything, right? So that can depend very much on the client, right? On what you're serving. How often are you on call? That depends very much on the structure of the company. Okay, if you end up with in a company that's only got 3 service guys, you can pretty much guarantee you're going to be on call every 3rd week, right? And you might be backing up the other guy half that time. You know, you're not on call. That's possible, right? You go to work for a company that's got 6 guys. That's probably a more common setup. Is a 6-man rotation. You know, every 6th week, 4th week, 6th week, something like that is kind of an industry standard. There's definitely exceptions to that, right? But that's the general idea. Okay, we do have to provide coverage 24/7. Another piece that might be a little different is the urgency. Okay, residential guys might get 6 calls in a day, might run 4 of them. You know, 2 of them you couldn't get to, right? I'll see you tomorrow. Okay, supermarket guys aren't going to do that. They may only get 1 or 2, but they got 2 hours to get there because the whole rack's down, right? I got $250,000 worth of meat going bad. So it's an emergency, right? So I'm going to drop whatever I'm doing and I'm going on that call now. And it doesn't really matter what I had going on, right? That can happen. That's not the majority of our calls, but it does happen, right? The majority of our calls are more along the same lines as an AC guy. I've got a freezer door, you know, in the back hallway for a walk-in, and it's dragging, right? So we're kind of leaving it half open, half closed. Can you come adjust this thing? Yeah, tomorrow or the next day, you know, because I got these other emergencies, right? So we prioritize our calls. Okay, that's a little bit more along the lines of the service tech. And then this last one I want to talk about is a startup tech. So what's a startup tech? Well, a startup tech is a guy who knows this system well enough as a service tech, right? He can handle just about anything that would go down or not work, right? But unlike a service tech, he's part of that installation team. He's the guy with all those guys who set cases and don't have an EPA card and don't know how it works. He's the guy on the job that does, right? So he's pulling a vacuum. He's the guy that's charging systems. He's the guy that's making sure when they flip the switch and everything comes on, that it functions correctly. He's checking that superheat. He's dialing in that EPR, right? All right. So he's the service guy of the installation world. So he lives the life with the installation guys, but he's the smart one. I mean, he's the, I'm looking at my startup tech over here. Brandon is one of my guys, and he is a startup tech. So really those are the 3 major opportunities to get into supermarket refrigeration. Couple opportunities if you're local here in Florida. Kalos, I'm sure you guys are aware, has a supermarket team. I do run that team, the startup guys and the service guys. There are a couple different models that can be used to do this. One of them is in-house. When you hear the terms in-house, what you're hearing is the owner of the equipment has their own team that fixes it, right? So when in-house is you're going to work for a retailer. Let's be honest, that's what they are, right? They know how to sell product, and they've got a lot of expense in trying to maintain their refrigeration. So they're trying to do that in-house, right? When we talk about vendors, we're talking about contractors, right? These are the guys that somebody else, one of those retailers, hires to come do this work. Are they hiring us for service? Are they hiring us for preventive maintenance? Are they hiring us for both? There's a couple different models for that. We can have what's called a contract. A contract would be the service provider, your company that you go to work for, gets paid a fixed amount of money every month for the number of stores that they take care of. And they take care of everything, right? Those type setups are very heavy on preventative maintenance. I can't afford to run emergency calls in the middle of the night and pay my guys time and a half. Because the contract doesn't allow that kind of cushion, right? So I'm going to have my guys instead prevent those calls. Well, this is better, right? Is this not a great idea? Right? It's a great idea as long as that dollar figure is correct and it covers that preventative maintenance and my technician's skill set is high enough that they're efficient, right? Then that works fine. If any one of those things gets out of whack, that's not really a great plan. Then the other version that you'll see is time and material, right? Just like it is in the residential world today. I'm going to charge you this to show up in your driveway. I'm going to bill you this per hour that I'm on the job, and I don't know how many hours it's going to be, right? Really common today is when we get a service call, we have what's called an NTE, right? You might hear these terms. Not to exceed is a price, right? So the vendor is going to say, I'm going to send you on this call, but if it is going to cost more than this dollar figure, you better call me. Let's have a conversation about it. If it's going to be less than that, just fix it, right? That dollar figure could be all over the map, right? Depends on how profitable, how much expense they have to spend. They're retailers, so they don't really care what's going on in my rack. They don't really even know, right? What they know is I got this much money to spend, I got this much time left in the year, I'm good, so I'm going to give you this full NTE, right? Or even worse, I've spent this much, I only had this much, and I got this much left in the year. My NTE might start shrinking. That's the reality of a supermarket technician, vendor, supplier, contractor. Anybody who services these stores is they're dealing with a retailer, right? Not uncommon for commercial air conditioning. The guys have the same thing. You walk up to that 27-year-old piece of junk with the rust it's falling apart, and you keep telling the guy, this is the third time I'm telling you, you got to replace this thing. He's like, yep, not this month. Go ahead and taper up. We'll talk next month. All right, it's not uncommon for that to happen in the supermarket world too. All right. Any questions about any of those trade jobs? Potential career paths. Yeah.
So say you want to go through the service side, is it kind of similar to maybe like residential commercial service recommended to go through installation and start?
Right. That's a good question. How do you get your foot in the door? That's kind of what you're asking, right? If you want to get your foot in the door for service, it can happen a lot of different ways. I will tell you the overwhelming majority of service technicians that work on parallel rack systems at one time were residential technicians. Right? That's pretty much where most of us started. That being said, were you a residential tech? See, yeah, I was going to say I got a couple guys that didn't come that route. So if you're doing residential right now, you can be on this path, right? That's kind of my point. The overwhelming majority of guys started that way, but it's not the only way, right? So another way. I've got an apprentice right now that was on the installation team. He was a case setter. Did a great job, right? Setting cases. Was picking that startup tech's brain every time that guy stopped for a minute. Hey, what are you doing? What's in your head? What are you thinking about? How's that work? Got interested in it, right? Went and got his EPA card, and he's an apprentice now for our startup team. Couple guys that recently graduated with Brandon. Same story, exact same story. Did not have previous experience. Is it possible? Yeah, it is. It's just not traditional, right? The more traditional way that you end up here as a service technician from a residential guy is you start looking for commercial. If you haven't touched much commercial, you're going to want to, right? Not because it directly relates, doesn't necessarily, but the thought process, the learning, and the troubleshooting does. And this is what I mean. If you walk up to the same Say you're a Bryant manufacturer or dealer, right? Every freaking unit you look at is one of these 3 models of Bryants, right? You get pretty good at fixing that Bryant. You may not really understand why. You know that I always have this problem, so I'm going to go attack this problem. You get kind of lazy with your troubleshooting because I've seen this 27 times. I know this is the 28th. Not going to go through that troubleshooting process, right? When you move into that commercial, you start walking up to really unfamiliar equipment, stuff you have never seen before, right? Because there's gazillions of versions out there. You're going to hone in on that troubleshooting ability. You're going to really understand how that refrigeration cycle works, how the controls work, how to troubleshoot a wiring diagram. You're going to start working through all that stuff because you have to, because this is completely unfamiliar, right? Guys that can do that are able to work in that commercial world, start working on 3-phase power, right? Start getting exposed to some of these things. Guys that are able to really take hold of that and get excited when they walk up to a new piece of equipment they've never seen before, rather than terrified. Those are my guys. That's who's going to be in the market world, right? So go do that. Commercial is to me the light version of moving into racks. Get into commercial and then try to get some exposure to some restaurants, some convenience stores, right? They have small refrigeration. It's really simple stuff. 1 compressor, 1 evaporator, right? And use that concept that I was just giving you about the suction pressure equals my boiling temp. Nail that down. Get that nice and solid. You'll start seeing some liquid receivers on those setups too. And so you'll see critical charge no longer applies, right? How do I control this? How do I control that? Work through those things. When you get that down pretty well, yeah, now you go knock on somebody's door who's hiring supermarket guys. Tell them I'm green. I don't know your supermarket, but here's what I do know. And you start rattling that stuff off, you'll get a job, right? They'll give you a shot. Okay. If you walk up to that same vendor and you don't know what you're talking about, yeah, he's going to send you on your way, right? So you gotta, if you're going to come into it that way, you got to be pretty solid on troubleshooting unfamiliar equipment. That's really the key. Being able to troubleshoot unfamiliar equipment, read a wiring diagram, get a class on that. If you don't know how to do that, you're not comfortable with that. It's not uncommon. It's not uncommon at all. Just be sure you do, right? Follow up on that. And really understand the physics of this refrigeration cycle, because I got a lot of pipe out there and I have no way to look inside that pipe. I have a pressure gauge, I got a temperature gauge, and that has got to tell me what's happening inside. That means I have to understand the physics of what's supposed to be happening, right? Am I at saturation? Am I superheated? Am I subcooled? What does that mean? How do I measure it? Is that what's happening in this pipe, right? Make sense? All right, I think that's about it. All right, thank you very much. Enjoy your day.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community, for techs, by techs.